Hi, today we are going to study this HSI, an horizontal situation indicator. So this one was installed in a Harrier attack aircraft according to the seller. As you can see, so there is a broken glass here, so this is why this one was not very expensive. We can suppose that this thing was removed because of this broken glass, so this thing should work. So the weight of this item is approximately 2 kilos, 2.2 kilos exactly. Okay, you can see the part number of this unit. The catch code is 10138, corresponding to a company called Astronautics, located in USA, serial number 1146. So there is a connector with tiny pins. This will be a little bit complicated. It is not a standard connector. And another difficulty is that this thing seems soldered here. Very nice unit. Okay, we can see a differential gear. There is another one. And several electronic boards. Okay, so we have here the compass card. Okay, and the feedback element is here, so this is a control transformer. Okay, so the input of the compass card corresponds to the stator of this control transformer. And anyway, it seems that, okay, so we have another one here. So this is for the course. Okay, so here we have the power supply transformer. Okay, so we have two coils here, so probably we have the power supply input here. Now we can see that there is a hybrid module here. When you want to do the reverse engineering of such a thing, the first thing to do is to locate all elements. We have motors, synchro transformers, resolvers, and so on, and to identify the linkage between each element here. So it is what I did on this diagram. We can see that we have three blocks. One block corresponds to the course. There is, of course, a DC motor. there is a differential resolver, but actually this is a synchro, and there is a resolver. The second block corresponds to the compass card. There is a DC motor and a differential resolver, which is actually another synchro. And we have a third block corresponding to the bearing pointer. There is a motor and a resolver here. The linkage can be differential, gear train, and other things. On the top, we have the electromechanical block diagram corresponding to the VOR bearing pointer. This is an interesting feature. The bearing pointer is set using an ARINC 429 interface corresponding to the VOR bearing. There is a digital to resolver converter, and the output here is fed to the stator of this resolver, and there is a servo amplifier connected to the motor. The last thing concerns the course. This is also an interesting feature. The course input here is a synchro. It is connected to the differential resolver, which is actually a synchro control transformer. It is also possible to change the course manually using this knob. There is a differential for that. In that case, the motor should be inactive. And in that case, you can change the angle of this shaft using this course knob here. And of course, the course is also relative to the compass card. This is why there is a differential here. On the top here, we can see the servo control loop for the VOR bearing pointer. Pointer is linked to this motor. There is here a resolver. The stator of this resolver is connected to the digital to resolver converter. During the reverse engineering, I have noticed that this winding is open. Therefore, this resolver is defective, but there is a workaround for that. There is a second winding which is not used. Therefore, it is possible to use this winding instead of this one. There will be an offset of 90 degrees, but it is possible to compensate this offset by changing the position of this resolver. Also, there is a design error concerning this filter, which is not connected for this servo amplifier. There is a resistor in parallel to this inductor in order to have a damping. This indicates a lack of verifications of the design. Okay, we can see here the bad routing. So you can see the filtering coil here and the damping resistor. The output is this line here. It is connected here to the output of the amplifier, which is pin 8 here, this hybrid. Okay, so normally this track should be connected to that point. Here we have the servo control of the compass card. So this one is straightforward. We have here the differential resolver, which is actually a transolver. So this is the common arrangement. On that unit, this voltage is used to activate the flag of the compass card. Generally, the flag is activated when there is a very small voltage at the input of this amplifier. And by the way, these amplifiers are power op-amps. So there are two inputs here, and you can see there is a feedback. The last thing concerns the course. This is the most interesting feature of that unit. The course can be set manually. It is not shown, but there is a differential gear which permits to modify the position of the course using a knob. Otherwise, the course can be set using a synchro transmitter connected to this control transformer. You can see that the course is also linked to this differential. On the stator, we have the sin and cos corresponding to the VOR bearing, which is set using an ARINC 429. On the rotor, we have voltages corresponding to the difference between the VOR bearing and the course. This voltage is converted into a DC voltage using a synchronous detector, and the result is fed to this galvanometer, which indicates the deviation between the VOR bearing and the course. This voltage is null when the course is identical to the VOR bearing. One dot corresponds to an angle between 2 and 3 degrees, I don't remember exactly. And the second winding corresponds to the cosine. When this needle is centered, we have a maximum voltage, and this voltage is used to set the to and from arrows. Okay, it is not visible because this arrow is masked by the front plate here, but there is an arrow which is located somewhere here. Okay, you can see. Okay, you can see this arrow here. Okay, so we have 2 on the top row and from when this row is on the bottom side here. This unit is more than an HSI. It's an HSI plus a part of VOR function. We can see on the screen the schematic of the VOR bearing setting, which corresponds to these 2 boards. This hybrid here corresponds to the ARINC 429 front end. It is this part here. There are 2 inputs and several outputs. One output corresponds to the clock, second one to the data, I don't know which one. And there is another signal here, which is maybe a synchronization clock or something like that. The second hybrid is the ARINC 429 decoder. It's this part here. We have the data output on the right, and we have 8 lines here, which are actually the label configuration. Some of them are connected to ground, and others are connected to the power supply. If we complement this byte, we find in octal 222, which is the label for the VOR bearing. The data bus here is connected to a third hybrid, which is this part here from Natel with an obscure reference. I didn't find any documentation regarding this part, but the reverse engineering shows that this part is obviously a digital to resolver converter. There are 2 outputs here and 2 inputs for the reference, of course. These 2 lines are connected to the power supply transformer. We have here 2 amplifiers with a gain of 2. These 2 outputs are fed to the resolver for the course. We have 2 voltage followers, and these 2 outputs are fed to the second resolver here. The shaft of this one is linked to the course. We have here a first phase detector connected to one winding of the resolver. The output is amplified, and the output is fed to the galvanometer for the course deviation. This resistor permits the calibration of this galvanometer. Okay, so this resistor is here, 2K21. The second winding, which is orthogonal to this one, is fed to the second phase detector. The output is filtered here and is fed to this comparator, and the output is fed to this solenoid, which permits to have the from and to rows here. And here we have a crude comparator. The signal comes from the transformer, and there is on that collector a square wave at 400 Hz. On this page, we have the circuit for the DME. It corresponds to this board. We have the same hybrid, which is the ARINC 429 decoder, which is here. It is connected to this ARINC 429 front end. And we can see here the configuration of the labels. If you complement this value, you find 201 corresponding to the DME label. And we have here 4 BCD outputs. The maximum value for DME is 3999. But you can see on that unit that we have only 3 digits here. It was impossible to have a 4th indicator here because of this cylinder assembly here with the gears. Okay, we can see that we have a solenoid which permits to activate a decimal dot, which is this solenoid here. Actually, this unit has 2 ranges. The first range from 0 to 99.9 miles, and there is a second range from 0 to 399 miles. The selection of these 2 ranges uses the 2 MSB bits here, corresponding to the leftmost digit, 0 to 3 normally. If we have 0, only the 3 rightmost digits are used, from 0 to 99.9. In that case, the decimal dot is activated using this circuit. We can see that if these 2 lines are at low level, this transistor is off, this one is on, and the decimal dot is activated. This signal permits to select between the low or high range. The selection is done by sensing the current flowing through the solenoid. If the decimal dot is activated, this transistor is on, this one also, and we have a low level here. So we have this arrangement for a particular reason. The reason is if we have an open solenoid, in that case the decimal dot disappears. For example, if the distance is 25.5 miles, in that case the pilot will see 255 miles, which can be problematic. So in that case, if the solenoid is open, this transistor will be off, the high level will be present on that line, and the second range is activated, 399 miles. In that case, a value of 25 will be displayed. It is better to display 25 instead of 255. We can see here on the right 3 BCD to decimal converters, which permits to drive each digit here, and we can see that we have 3 multiplexers. When the 399 range is activated, the first decoder here is connected to D4 to D7, therefore the tenth of mile digit here is lost. The second digit is connected to this BCD output, D8 to D11, and the leftmost digit is connected to these 2 bits here, which permits to display 0 to 3. Otherwise, the first digit is connected to the first BCD output, the second digit to the second BCD output, and the first digit to the third BCD output. There is a kind of auto range. It is a nice feature, and here we have the activation of the DME flag. If one of these 3 signals is at high level, the flag will be deactivated. Before testing this unit, I will repair this defective synchro. This one, you can see the yellow-white wire from the second winding, which is not used. So this wire is here. You can see that it isn't connected to anything. I will solder another wire here, and I will connect directly to the input of the servo amplifier, actually in parallel here, because this one is open. This winding is connected to the input of the servo amplifier, and I have connected also a synchro transmitter for the compass card. We can see the synchro transmitter here. So let's turn on the power supply. We can see that the compass card works, and you can see that the VOR pointer is initialized to east instead of north. So now I will rotate the resolver 90 degrees counterclockwise here in order to have the pointer aligned with the north at startup. The resolver is this one. Okay, perfect. I have modified the code of my ARINC 439 test set in order to send the DME miles label 201 and the VOR bearing label 222. The increment for the VOR bearing is 15 degrees. Let's start with the VOR bearing. So shift 2, the first value is 15 degrees. Okay, you can see that this thing works, and you can see that this bar is centered when the VOR bearing is the same than the course. One dot corresponds to 4 degrees approximately. So now let's see the DME miles. Shift 1. That's all for this indicator. Bye bye.